Hey guys! Today we are going to talk about the fluid compartments. We did have this class before, so this video is supposed only to make sure you understand the most important things about fluid compartments. Well, when we're talking about fluid, the first thing that comes into our minds is water. And we do have to tell you guys that around 60% of a body weight in an adult man is water, which for a median man that is around 70 kilograms gives you about 42 liters of water. I do have this mark here because this is for adult men. If you're talking about women, for instance, then this percentage is lower. It's about 50%. And in elderly, this percentage is even lower. It's about 45%. Well, anyway, if we take this 60% and split it in 40 and 20, then we have that 40% of the adult man body weight is within intracellular space, and about 20% is in the extracellular space, which gives you about 14 liters within the extracellular space. This extracellular space we split in two compartments: the interstitial space and the plasma. Around 70% or 75% of the water within the extracellular space is within the interstitial space, and around 25% is within the plasma. So if you're thinking about a 70 kilogram man with 42 liters of water, 14 liters is within the extracellular space, and only 3.5 liters is within the blood. However, we have 5 liters of blood because in the blood, of course, you also have the cells. So the total blood is around 5 liters in this man. The next question we have to ask us in order to understand the fluid compartments is what split them? So what splits the compartments? Well, if you're thinking about intracellular versus extracellular space, then we have, of course, the plasmatic membrane. So this is easy. When we are talking about what splits the interstitial space and the plasma, we have the wall of the capillary. And in the wall of the capillary, we have pores, which are like big, well, they're not big actually, they're pretty small, so sorry, but they're very small places in which you can pass water. Okay, so water can pass really freely between plasma and the interstitial space. Then again, we have to think we're not only talking about water. We're talking about very small molecules. So what goes through the capillary pores? What do you think? Well, if we're thinking about very small molecules, then of course ions can pass through it, not only water, and also very small molecules of other stuff like CO2 and oxygen and urea, glucoses, and this kind of stuff. Also, very small proteins can go through these pores, but like cytosines and these kind of things. But you have to keep in mind that they are very, very small. Most of our proteins are bigger than that. So most of our proteins within the plasma really don't pass through these pores, okay? And another thing that is very interesting is that in the plasma we have a little bit more proteins than we have in the interstitial place. Sorry. So in that sense, when we think about things that go through plasma and interstitial place, space, what we really have in common is that the ions and water can pass freely between these pores. However, when we are talking about the plasmatic membrane, that's not true. You know that the plasmatic membrane is a bilipidic membrane that is very selective. It really doesn't let any molecule, even if it's very small, to pass if it has if it's positive or negative. Well, because of that, we will have the potential of the intracellular space being very different from the extracellular space regarding ions. Okay, we of course have a lot of difference between intracellular and extracellular space regarding proteins, and also there is a lot of difference between the interstitial and the plasma space regarding proteins as well. Okay, but when we're talking about ions and water, then interstitial space and plasma space, we really think it's the same. Okay, so we only have to think about the difference when we are thinking about ions. We only think about extracellular versus intracellular space, because plasma and interstitial space have the same composition. Okay, well, since we have the bilipidic membrane that is highly selective, well, anything that wants to go inside the cell or outside the cell has to go through transporters. Okay, and if we think about transporters, then we really have to think about three ways of the substances to go through the membrane. When we have small molecules that are not electrically charged, they can simply go through the membrane. So like CO2 and oxygen and alcohol, there is no problem for these molecules just to go through the membrane. Another thing that is interesting is that I do know that you guys have the concept that water can pass freely within the membrane. It's true, water does go freely through the membrane, but it's not like through the lipids, the bilipidic membrane. It's not between the lipids, because of course water is lipophobic. So what happens is that water and urea, both of them, they go through any channel, you see, because it's very small, and the molecules that are going inside or outside the cell, they usually are hydrated, so they take the water with them and go, and then the water is able to go inside or outside the cell freely. It's not like a real freely, it's because of these kind of channels. Okay, well, so we do understand the simple diffusion. We do understand that some substances can seem like they go freely, but they actually take in channels. But ions are very carefully transported. Our cell is very concerned about the levels of sodium, potassium, and other ions. This is because these kind of ions are very important for movements and potential of the membrane. So the cell is very careful about that. And how does the cell make sure that the concentrations of the ions are kept in the way that the cell needs? Well, this goes, when we're talking about ions, this goes because of the active transports and the channels. So first, to understand the active transports, we have two kinds of active transports. We have primary and secondary. When we're talking about active transports, we are talking about the substance going against its gradient. So you have to spend energy in order to put this substance inside the cell or outside the cell, because it's going against its chemical gradient. So we have the primary kind of transportation that uses a pump, and the most famous pump that we have is the sodium-potassium pump. It puts the sodium outside the cell and the potassium inside the cell. We also have the secondary active transportation. This kind of transport is very clever. It uses the gradient of another solute as energy in order to put the other solute inside the cell. For instance, we have a active transportation like this that uses the sodium gradient that makes the sodium like want to go inside the cell because it's highly concentrated in the extracellular space. And so it uses this energy of the sodium wanting to go inside the cell to put the calcium ion also inside the cell. So this is an example, but we have lots and lots of different kinds of secondary active transportation. We call it an active transportation because it requires the sodium-potassium pump to work. If it doesn't work and it's not spending energy, then the secondary transportation also wouldn't work. Okay? So now we understand the active transportation, we understand the simple diffusion, and we understand the substances that goes through the channels with like simple diffusion, but not freely through the membrane. But we have to talk about how sodium and potassium and other ions can go inside the cell, also following their gradient, okay? But not in order to transport another substance. So like we have some kind of sodium channels that open in the membrane of the cell only in order to put sodium inside the cell. That's his goal. He wants to put sodium inside the cell. But you know that the body have a lot of trouble in order to put the sodium outside the cell. So why would it want to put it inside? Well, only some kind of cells have this kind of transportation, and it's mainly used for the electrical potential of the cells, and you will understand that in another class. So we do have sodium, potassium, and calcium and other ions channels that really just want to put that ion inside or outside the cell through its gradient, okay, following its gradient. Well, and we also have another kind of transportation that is called facilitated diffusion. This is a very interesting thing. It puts a substance inside or outside the cell following its gradient, okay? So it's like a channel that allows something to go inside or outside the cell, but it's not a simple channel. It actually changes the protein structure in order to take the other substance inside the cell. And this is interesting because this limits the amount of substance that can go inside the cell. It's not like purely defined by the gradient. No, it also depends on how this protein manages to change its structure in order to put this substance inside or outside the cell. One example of this kind of transportation is the glucose transporters. They are only able to put inside the cell a certain amount of glucose, and this is really smart because think that you just ate a chocolate. If you just ate a chocolate, then your intestine, your bowels are going to absorb all that glucose, right? And if our body worked with glucose only like through gradient, then when this blood really went from the balls inside your liver, all your glucose would go inside your liver and there would be nothing left for the rest of your body. So this is very smart. This is the interesting thing about a facilitated diffusion. There is a limit. So now that you understand the kind of transporters, you can even imagine the kind of differences you have between ions when you compare the extracellular with the intercellular space. If we have the sodium-potassium pump, then we have a lot of sodium outside the cell and a lot of potassium inside the cell, right? We also have differences in calcium and magnesium, but it's by far not the importance of the difference between sodium and potassium. And when we are thinking about the anions, then the most important anion in the extracellular space is chloreto, and in the intracellular space we have proteins. You have to remember that proteins have that radical that is connected with the carbon, with the alpha carbon, and most of our radical chains are negative, are charged negatively. Okay, so since we have more protein in the intracellular than in the extracellular space, we have more proteins responsible for the negative charge. We also have phosphaten, which makes a lot of sense because inside the cell you have ATP, and ATP is mainly formed by potassium and other organic anions. So the composition of the intracellular and the extracellular space is very different regarding ions. Okay, so when we think that the ions are really different and that the proteins are very different, but we also know that the water can go freely through the membrane. So if the water can go freely through the membrane, then it doesn't matter what kind of solute you have in these compartments. The osmolarity of the intracellular will be the same osmolarity of the extracellular space, because if you do have a problem that your intracellular space gets too much osmolarity, then the water just goes from the extracellular space inside the water, right? And the other way around is also true. If the extracellular space gets more osmolarity, then the water goes from the intracellular space to the extracellular space freely. Okay? So this concept is important because then if you know the osmolarity of your plasma, automatically you know the osmolarity of all your cells in your body. Okay? So within the plasma, when we look at these ions, it's really easy to see that sodium and chloreto must have a very important impact in osmolarity, right? So yeah, they do. When we calculate the plasma osmolarity, we just multiply sodium by 2, because when we do that, we are considering the chloreto and also the bicarbonate and other anions. So this is responsible for most of our osmolarity in the plasma. We also have two other molecules, glucose and urea, that also are important for osmolarity, but you can see that their importance is really it's really lower than the sodium, because the glucose level you have to divide by 18 and urea level you have to divide by 6. And the reason why we do this division is because we want the osmolarity. We want how many particles you have when you have glucose in your blood. You want to know how many of them are not connected to another particle. This is osmolarity. So since we measure glucose in milligrams per deciliter and not in osmoles, we have to divide it by 18 in order to correct the kind of measurement. The same thing for urea. We dose it in milligrams per deciliter, and we have to change it into osmolarity. For sodium, we don't have to divide by anything because we measure it in plasma in milli equivalents for a liter. And since each molecule of sodium has one charge, we have that the osmolarity is the same as the milli equivalence. So you don't have to divide the sodium. So there you go. This is the formula for estimating the plasma osmolarity. This is important because, well, you could think, but teacher, why do you calculate it? You could do a exam and just measure it. Well, we could, but it's more expensive. So what we do is that we really calculate. This is important because when we calculate, we get that the plasma osmolarity is about 300 milliosmoles per liter. But if we do use the exam, then we would not get this value. We would get about 282. The difference is because not all molecules of sodium is split from chloretum, right? Some of the sodium still gets is together with the chloretum. So it's not true that you should multiply by 2. If you do use a correction factor, you get the number 282. But for practical reasons, we just know that there is this correction factor, but we understand that we use the value 300 with limitations. Okay? So in practice, what we use is really this formula. There is another thing that I would like to call your attention into, is that urea, I just said that urea goes through the channels of sodium and potassium and etc. Freely, because it's a small molecule and that's not electrically charged. So there is a kind of formula that takes out urea, because there is no difference between the intercellular and the extracellular space regarding urea, which is called effective osmolarity. So you could take urea out of the formula, but in medical practice we usually use the three parts. We use sodium, glucose, and urea. Okay, so this leads us to the discussion of the kinds of solutions that we have in order to treat dehydration. Since dehydration is the loss of water and sodium chlorate in the same proportion, you have no problems with the patient osmolarity, right? The patient has 300 milliosmoles per liter of osmolarity, and you don't want to change that. You only want to give the patient water and sodium chloride in the same proportion. So let's look into these kind of solutions and see which one of them helps us. Well, we have oral solutions. Oral solutions, they are taken orally, of course, and our bowels are responsible for absorbing them. And you have a kind of safety because of that. because since your bowels are absorbing them, and that's not a fast process, it takes a while, you have a chance for your body to really adapt into what you are absorbing. So you will have in further classes that the main hormone, the main responsible for our osmolarity regulation is the antidiuretic hormone, ADH, right? So in order for a person to have a problem with osmolarity, she always has to have overcome the possibility of ADH doing its work. And when you take oral solutions, since it is a process that takes a while in order to absorb, then you have all the possibility of ADH to work. Okay. For physiological saline, it's sodium chloride in this concentration, 0.9%. It has 154 milliequivalents of sodium and of chloretum, and water enough to have an osmolarity of 308. Oh, if you use the correction factor, then it would be 286, but still. So as you can see, the physiological saline has a osmolarity that is really close to the plasma. This is why it's called physiological saline, okay? But it's actually a little bit more concentrated. It has a little bit more of osmolarity than compared to your plasma, okay? This is important when you use huge amounts of saline. If you use like liters and liters of saline because of a patient that is really not doing well in the ICU context, then you could have an issue with this a little bit more of osmolarity that you have, okay? Because ADH may not be enough to overcome what you've given in physiologic saline, especially if you give it too much, and too fast. Well, as for lactate ringer, in English they only call it ringer. Well, it has about 330 milliequivalents of sodium, so a little bit less than your plasma. It has about our plasma has about 135, and it has an osmolarity that is close to the plasma, but a little bit. This is for already with the correction factor, okay, but a little bit less osmol, but it's a very good option to hydrate the patient because it has a lot of sodium, a lot of chloretum, and the osmolarity that is pretty close to the plasma. So since it's kind of similar to physiological saline, what's really the advantage of using the ringer lactate? Well, the advantage is, of course, the lactate. The thing is, when you give physiological saline, you're giving a lot of chloretum, much more than you give when you give ringer. And chloretum is, of course, a very strong acid. It can go close to your plasma proteins and steal the hydrogen from them. So now you have chlorhydric acid. So this is why the pH of physiological saline is about 6.2 when our plasma is about 7.4. So when you use physiological saline, you have two problems: not only the osmolarity, but also the pH. So when you have to use a lot of volume in a patient, you may start with physiological saline, but in a second moment, just hours after, you try to use the ringer in order not to have your pH too low and in order to not have your osmolarity increased. And then we have the polyelectrolytical solution. Well, as its name says, it has a lot of electrolytes. So really what it wants to do is to give the patient a lot of electrolytes that it thinks that the patient lost. So if you do work in a place where you are not able to measure magnesium and potassium, and you do have a patient that has lost a lot of fluids like diarrhea or vomits and etc., then you could use this kind of solution, imagining that you're giving the patient everything that he lost. Okay, but if you are working in a place where you are able to measure all these electrolytes, we usually prefer to measure them and give the patient only what he's really missing, not everything. This solution is also interesting because it really has a similar osmolarity with the plasma, and it doesn't have a too low pH. Of course, it depends on the kind of polyelectrolytical solution that you're using, but it has a nicer pH than physiological saline anyway. Well, so if you do have a patient that has severe dehydration, then you have to use an expansion phase in order to make him improve faster. And we usually prefer to use the physiological saline, but if you do have to give a lot of volume, if you do have to repeat that or do a too long maintenance phase, then you would start to think about lactate ringer or the polyelectrolytical solution, depending on what kind of resource you have to measure the ions of the patient. So after the expansion phase, as we were saying, you do have to have a maintenance phase, because all that you give intravenously goes to the plasma. It takes a while in order for it to go to the interstitial space and inside the intracellular space finally. So it might take hours in order for you to really have the fluid that you want inside the cells. So you only do the expansion phase in order to recover the patient rapidly, especially if the blood pressure is low. And then the maintenance phase, you take it easy in order for your cells to have time to absorb all of that. And it's really nicer in medicine when you can do things nice and easy, because you do have the opportunity to give the body opportunity to adapt to what you're giving. So you have the time for the ATH hormone to really make sure that the osmolarity stays regular. So it's nice to do things slow. When you do have a problem with osmolarity, that really usually involves sodium. You can have problems with osmolarity when you have glucose levels too high, that's true. But the most common thing that may change osmolarity is really sodium. So we have three kind of solutions that you could use to change the plasma sodium concentration. You could use saline solution 3%, which has like much more sodium than the physiological solution, and has an osmolarity of 940, so it's like a lot. This kind of solution, you really should take a lot of care if you're thinking about giving it intravenously. You really should think about doing this very slow, otherwise you can really have a difference between osmolarity in the intracellular and the extracellular space too high. You may have a difference of 940 in the extracellular space and 300 in the intracellular space. This is not good. So try to do things slowly when you are dealing with sodium. And you do have the glucose 5%, which has glucose 50 grams in 1 liter of water and has a osmolarity of 252. But this osmolarity is really not true, because the glucose, once you give it intravenously, it goes inside the cells, and because of insulin, of course. And once it is inside the cell uses it for energy. So in like a few minutes or hours, your glucose has all like gone, and the only thing that you really have given the patient is water. So it is a hypoosmolar solution, but that you give slowly, and also that turns into a hypoosmolar solution slowly, because the glucose takes time to go inside the cell. So this is a very interesting option when you have a patient that has high osmolarity. You can help him decrease his osmolarity by giving glucose 5%. Okay? When you have a patient that has high osmolarity because of the concentration of sodium. Well, of course, this solution at 3% is used for patients that have a low osmolarity with low sodium, right? We also have the distilled water, which is like pure water. It has like 0 osmolarity. We really should not use this intravenously, because this such a low osmolarity makes this solution, this water actually just want to go inside the first cell that it sees, and the first cells that it sees when you put it intravenously is the hemácia. So it makes hemolysis, and you really should not use it. We only use distilled water in order to dilute medications, because if you're diluting medications, then of course the osmolarity increases. So these are the kinds of solutions that may change the concentration of sodium, and therefore the main factor that involves osmolarity. And although we have 3, you should never use distilled water. So for this class, this is what I wanted to discuss with you. I know that this issue is not easy, and if you do have any doubts, of course you can talk with me in the other classes. See you in the next video.